the seminar and also post the slides on our website as well. But please feel free to break in at any time and ask a question. So I'll start talking now, just give you a very, very brief introduction to ATA Engineering. We are primarily an engineering consulting company, work in design analysis and test of highly engineered structures. Our group has been together for over 30 years, and we have a lot of expertise in Nastran. But this particular seminar is through our business as a VAR for Siemens PLM software's CAD and CAE software, in particular NX Nastran. There are two links at the bottom of this slide. The first, the ata-e.com link, is to ATA's overall website that primarily describes our consulting services, and the lower link is specifically for our PLM software VAR business. So this presentation, the recording of this presentation, and also the slides themselves will be available on that website after the presentation. So what I hope to cover today is to give a brief summary of some of the major factors that control Nastran performance. The fact is that there are a lot of things that control Nastran performance. It's problem dependent, it's dependent on the computer that you're running on, and there's really no way that I can cover all aspects of Nastran performance. But I hope to give you some tools to try and understand what it is that controls Nastran performance, where the bottlenecks might be in your performance, and hopefully give you some understanding of some of the things that are going on in Nastran that you might not have been aware of. One of the few things that we'll cover, we'll talk a lot about I/O speed, because I/O speed is one of the things that is most important for Nastran performance. We'll talk about the two different versions of NX Nastran. That's the LP and the ILP version of Nastran, and understanding which one you're running and how that affects performance. We'll talk a lot about the FO4 file. The FO4 file is effectively Nastran's profiler output. It tells you as you run Nastran and after you've completed Nastran, it gives you a summary of all the performance aspects of the run. And I'm not going to talk a lot about HPC clusters specifically, but certainly what I talk about here will be relevant to that. If we have time, we'll get to talk about direct versus iterative solutions, and if we have time, also talk about parallel processing. Some of those slides are on this presentation. We may not get that. But the real goal here is to give you tools to try and understand what it is that's controlling the performance of Nastran jobs in your particular environment. To a large degree, Nastran performance is governed by I/O speed. Nastran was written quite a while ago when memory was relatively expensive, and Nastran is very good at not using a lot of memory and doing a lot of I/O instead. So to a large extent, Nastran is performance by the I/O speed, and specifically, there are 3 files that Nastran writes data to during the run, which are the files where typically most of the data is run. And we'll talk about those files. The first file is the database, which actually consists of 2 files, a master and a deball file. That's the file that Nastran leaves at the end of the run by default, and that would allow you to restart. So that would be data that would actually be useful for a restart. There are 2 other files. There's a scratch file. That's the file that Nastran is writing to continuously during the run, but the scratch file is where it stores data that it's going to need as it moves from one step in the program to the next step in the program. And then it has a separate scratch file it calls the SCR300 file. That's a scratch file that's used within a module. So for instance, if you are decomposing a matrix, while you're decomposing the matrix, the I/O that's required during that decomposition is written to the scratch 300 file, whereas the decomposed matrix itself is written to the scratch file. So the most important thing about Nastran performance, and if there's one thing you learned today, it's that getting I/O speed, in particular to those 2 scratch files, because if you actually look at where Nastran does most of its I/O, it's to those 2 scratch files. Being able to write quickly to those scratch files, and we'll be talking about some tricks for doing that, is one of the keys to getting fast Nastran performance. The other files for Nastran, there's an input file, sometimes called a .dat file or a .bdf file. There's the FO4 file. We'll talk about that. That's effectively a profile of the Nastran run. The FO6 file is where you would, as a human, would actually go and kind of look for summaries of output. The punch file, which is another ASCII file, is output. And then the output2 file, which is the most common file, binary file for results. But these files are all typically small compared to the scratch files and the deball file. So the first thing, before you understand much about Nastran performance, and this is something that I find a lot of people are not aware of, is that NX Nastran comes in two flavors. There's an LP flavor and there's an ILP flavor. The LP flavor has been around for many, many years. It does do double precision arithmetic, meaning it does 64-bit arithmetic, but it does it with 4-byte integers. And this, again, is somewhat historical. So there are a couple limitations to it. The major limitations of the LP version is that the most memory that you can actually access with that, because of the size of the integers, is 8 gigabytes. So when you're running the LP version, and most people are running the LP version, you're limited to 8 gigabytes of RAM, and that's total memory. So on most modern computers, even on most desktops, even on most laptops these days, we have more than 8 gigabytes of RAM available. So the Siemens team is transitioning to the ILP version, and my understanding at some point in the future it will be the only version, and we'll avoid this confusion from then on. The ILP version uses 64-bit integers and 64-bit floats. And because of that, it addresses a very large amount of RAM. I'm not sure exactly what the number is, but it's more RAM than anyone's likely to have for quite a while. So if you want to figure out which version you're running, if you actually look at your installation of Nastran, you'll see that there are two executables. This is on Windows. You'll see one called Nastran64.exe. That's pointing out that it's a 64-bit version of Nastran, but that is not the ILP version. And then there's a 64L.exe. So these are the command line versions, and on Linux, what you'll see is you'll see one just called Nastran and one called Nastran64L. So you need to understand which one of those you're running. And on Windows, there's really two ways to run Nastran. You can run Nastran from a command line, and typically most people will set up some kind of alias for this, in which case you would actually execute the Nastran command directly, and you'd be executing one of these two Nastrans, or you can actually have it pop up a little window where you select the file. Either one of those can be used to run either version of Nastran. So if you're using the one where you pop up the window, you want to make sure to use the 64LW as opposed to the 64W. Note there isn't much performance difference between the two versions of Nastran, and in fact the ILP version in some instances is slightly slower because the integers are larger. However, the real advantage of the ILP version is the ability to access more memory, and we'll be talking a little bit about how accessing more memory allows Nastran to run faster. Some larger models, in fact, require the ILP version to solve, but you actually have to have a pretty big model before Nastran will not run in 8 gigabytes of RAM. The key difference is, and the reason you recognize it, is Nastran, all the memory in Nastran, a lot of the memory in Nastran is referred to in words. And the meaning of a word in Nastran is different depending on whether you're running the LP version or the ILP version. So in the LP version, you have 4 bytes per word, and in the ILP version, you have 8 bytes per word. Other things to watch out for is that there are circumstances where you're transferring files from one version to the other, and the most common one of these is external superelements, where there will be some confusion as to the precision of the output. If you've executed a Nastran run and you don't know, or if you're running Nastran and you really don't know which one you're running, there's no easy way to tell. When you look at the FO6 file, you can't really tell which version you're running. You look in the FO4 file, you can't. The only place that I've found to tell which version you're running is to actually open up the log file and look for the word executable, and that will actually tell you which executable is being run. And for instance, on Windows, it'll say C, depending on where you installed Nastran. In my case, program file Siemens NX Nastran NXN9 64-bit NXN9, and this one here, the EM64 TNT is the LP version, and the TNT-L is the ILP version. And on Linux, it kind of looks the same. You can kind of tell based whether you got a 64 Linux or 64 Linux L version. So if you want to know which version you're running, take a look at the log file. So now that you're running Nastran, you're trying to understand performance. If you were to run any program, if you're a programmer and you're developing a program and you're trying to figure out where the bottlenecks in that program are and how you might make that program run faster, what you do is you'd run something called a profiler. And a profile will execute your program, and either function by function or possibly line by line, it would tell you how much time is being spent in each one of those functions or each line of code. Well, Nastran, every time you run it, Nastran is effectively running a profiler. So every Nastran run has profile output, which tells you exactly how much time and how much memory has been used for each step of Nastran. And that file is the FO4 file. So what the FO4 file is Nastran is executing a program in a language called DMAP, and as it runs through that program line by line, for every line of that program, it will tell you a bunch of information about how much time each of those steps is taking. So if you're interested in figuring out your Nastran performance and what is slowing it down and what can be done to speed it up, the first thing you need to do is to learn how to read the FO4 file. And we'll look at lots of different information that's in that FO4 file today. It contains information on overall memory and disk usage, as well as a step-by-step summary of every line. So if you look at the file, there's a bunch of information up front, and then you'll see the main part of the file will start with something that says, for instance, daytime. That is actually the actual time of the day that it's running. Elapsed, that's the amount of times, that's the amount of clock time since you started the job. So for instance, I've left out a whole bunch of the file. At this point, it has been 1 minute and 15 seconds into the job. The I/O in megabytes, this will tell you exactly how much I/O has occurred up to that point. In this case, it was about 3.8 gigabytes. The delta, that's telling you how much I/O is occurring in this step. The CPU seconds, that's telling you how much CPU time is taken. So for instance, in this case, it's been 1 minute and 15 seconds. I've got 1 minute and 10 seconds of CPU. And the delta CPU, that's the CPU taken by this step. And the rest of it is only interesting typically if you're into DMAP. It'll actually tell you which line of the DMAP is occurring, which sub-DMAP it's occurring in, et cetera. And then if you have the diag 8 turned on, you'll get a bunch of information on matrix trailers, which is useful for debugging purposes. The other thing that's in the FO4 file is for certain of the steps, such as matrix decomposition, which tend to be the numerically expensive steps, you'll get a whole bunch of extra information. So for instance, in this case, I'm doing a modal solution. In Nastran, the eigenvalue solver is called read. So for the eigenvalue solver, it'll tell me the first thing it's doing here, because of the particular option I'm using, is it's decomposing the MXX matrix. It tells me the size of the matrix. It tells me the minimum memory requirement. If you've got less memory than this, Nastran will not run. But it also tells me the critical thing is it tells me the minimum memory required to avoid spill. This is typically how much memory you want. More memory than this for in-core operations is not typically all that useful. And then, for instance, as I come down here, this is the actual decomposition. In this case, it took 3.1 seconds of CPU to decompose that matrix. And it'll tell me at the end of it what the actual memory was to decompose that matrix. So if you're trying to understand a Nastran job, if someone tells you that a Nastran job took a long time to run, or you're trying to figure out why a particular Nastran job just took 5 hours to run when you didn't expect it, first thing to do is go through the FO4 file and find out what part of the run took that long. Because without knowing what part of the run took that long, you really have no idea of what can be sped up. So the next thing to understand about Nastran is memory and how Nastran uses memory. Because Nastran was written a while ago, and since it was written in Fortran, it does not dynamically allocate memory in the sense that some modern programs do. What it does is it allocates a block of memory, and then it divides that block of memory up into a whole bunch of different sections. And if you look at the front of the FO4 file, you'll see some output that looks like this. And this is telling you for this run, and this is the beginning of the run, it's one of the first things that gets written, how Nastran is allocating memory for this run. So if I look at this, the total memory here, the total NX Nastran memory limit in words, and remember a word depends on whether I'm using the ILP or the LP version. For the LP version, a word is 4 bytes. For the ILP version, it's 8 bytes. So if I take this number of words and I multiply by 4 or 8, that's the total amount of memory in bytes. And if I'm in gigabytes, for instance, I divide that by 1024 cubed. That's the total memory. So that's what I would request on the mem card. When I run Nastran, I say mem equals something, and I can request that in words and bytes and gigabytes, whatever. That's what I get. The default is starting in NX Nastran 10, was that it will request 45% of the physical memory available in your machine. So if I have a 32 gigabyte machine, that works out to about 25.5 gigabytes is what Nastran will request by default. And if you're running the LP version, it'll try and request that. It'll immediately kick back to 8 gigabytes because that's as much as available. So that is the total amount that you request. And of that total amount, what you do is you tell Nastran how much you want for some different pieces of that. And the 3 major parts of that total amount are the high core memory. That's the memory that's available for in-core solutions. So for instance, when it's decomposing a matrix. There's the scratch memory. I was wondering if there's someone maybe who's not on mute. Thanks. There's the scratch memory. The scratch memory is memory, it's a certain amount of memory that's actually allocated to write scratch files. So in fact, if you have enough scratch memory to store all your scratch files, those scratch files will never get written to disk. So it's a temporary storage place for scratch files, and in fact, it's more than temporary. It'll actually store the scratch files. So if you're running on a machine with a lot of memory, that can be fairly large. And finally, there's a buff pool. The buff pool is just a buffer pool that's used to buffer the memory. So you've got kind of these 3 sections of memory, and the way you tell Nastran how to do it is you tell Nastran the total amount of memory you want, you tell it the scratch memory, you tell it the buffer memory, and there are defaults for this. The defaults were changed in NX Nastran 10. The default, the total amount is 45% of the physical memory. 20% of that is allocated to scratch, and 20% of that is allocated to this buff pool. And that was, based on testing, that was determined by the Siemens team to be a pretty good default. The thing is, that default really doesn't know anything about the amount of memory in your machine and may or may not be appropriate. So what you need to do is understand the amount of memory in your machine and the jobs you have is how to use that appropriately. The default, so what we found is that to get the maximum Nastran performance, what you want is as much core memory as is required and not necessarily that much more. So you can look at your FO4 file from a previous job and see how much memory was required and not ask for that much more than that. Then you can maximize your scratch memory, and the buffer pool memory doesn't have to be as large. I mean, the 20% may work in a machine with small amount of memory, but that's too much on most machines. So you can actually go ahead, knowing the amount of memory in your machine, you can go ahead and optimize this. Unfortunately, there is no simple rule that's always going to work for every machine. The other thing to be aware of, which is sometimes gets you, is there's another keyword in Nastran called the memory maximum keyword, and that sets the maximum amount of memory request. The default is 80% of the RAM if you don't set it to something different, which is a pretty good default. You typically don't want to ask for more than that. But for instance, if you have a 32 gigabyte machine and you really want to get 30 gigabytes, you're not going to get that without resetting your memory maximum keyword. So the optimal memory allocation, as I said, what we found is there's not a huge advantage to allocating more memory to this core memory than is actually required to avoid spill. So if you were to look at decomposition, so you were to look at your FO4 file and look for parameters for sparse decomposition, you might see a few of these happening. It will tell you how much memory is required to avoid spill. Much more memory than that is typically not useful. Now, that's not always true. And in fact, this particular example, I've given an example. This happens to be an example where I've got a very, very dense mass matrix. And in the Lanczos solver, it is actually having to use a lot of words of memory. But what we found to optimize performance is that this amount of memory, and this amount of memory is given in kilowords, just to be even more confusing. So what I do is I take this number, multiply it by 1024 to get it into kilos, and then if it's an ILP version, multiply by 4. If it's LP, multiply by 4. If it's ILP, multiply by 8. That's the amount of memory. And you'll be surprised at how little that is. Even for relatively large problems, that's probably only 1 or 2 gigabytes. It's not a lot of memory. And one of the mistakes that we see people make is that just by throwing huge amounts of memory at a job, they think it's going to run faster. And in fact, the opposite happens, is what they've done is they've sucked all the memory available out of the operating system, so the operating system now is much less efficient in how it's handling the I/O, and Nastran's really not making much use of it. So there's not much use to excessive amounts of memory beyond for the high core memory. So to calculate memory, you start from the total, and the idea is to have as much as possible available for this scratch memory. So if, in this particular case, on my desktop, I happen to have 32 gigabytes, 80% of that's 25.6, right? So I could say mem equals 25.6 gigabytes. That's the same as the memory maximum default. It's actually 25.55 or something, I think. The buff pool, and the buff pool is this buffer, and that's in number of blocks, and having more than about 100 blocks doesn't really help. That's 50 megabytes. So having much more than about 50 megabytes, there's really not much advantage to that. The default's probably far too much. Right? So then depending on how much you need for high core, whatever's left, you can go ahead and allocate to the SMEM. And all these defaults can be set up in your RCF file if necessary. So at the top of the FO4 file is summary on how Nastran is allocating the memory. At the bottom of the FO4 file is information on how much memory was used and also on how much data was actually written to disk. And so, for instance, you'll see something here called database usage statistics. And it'll tell you for each one of these files, and it will tell you the allocated blocks, that's as large as it could possibly get. It'll tell you the block size, and that's often called the buff size in Nastran, and it'll tell you how many blocks you used and how big it was. And for instance, for each one of these files, in this particular case, you can see, for instance, the dball file never actually got very large at all for this run. The scratch file, actually, it got up to 450,000 blocks. Okay, each block is a buff size, or it's actually in megabytes. This works out to be 112,000 megabytes, or 112 gigabytes, roughly. It also tells you that I've actually transferred about a terabyte. In this particular run, it transferred a little over a terabyte of data. Okay. But Nastran what's important here is that Nastran has lots and lots of different units for defining memory. So if I want to figure out size in gigabytes, okay, first thing I need to know is the buff size. The buff size is the amount of memory that Nastran is kind of the chunk size that Nastran reads and writes memory to I/O, or reads and writes data to I/O. The maximum size that can be is 65,537. That, in fact, if you look up the installation, that is recommended for large runs. So we just go ahead and put that in our RCF files as the default. Okay. So if you take that, multiply that by the number of blocks, okay, and then that happens to be in words, multiply that by the number of bytes per word, which is either 4 or 8, and then divide that by 1024 cubed, it's going to give you the memory in gigabytes. Right, so after you've been looking at this for a while, you kind of get to do these calculations pretty quickly. So the above example, for instance, when we look at what's allocated to the dball file, it says I've got 2 million blocks. Each block has 65,537 words. Each word has 8 bytes. So I multiply that all together and divide by 1024 cubed. I can tell that I've actually got about a terabyte allocated to the dball file. Now that's a logical limit. That's not related to actual disk space. That's basically Nastran's way of being nice and saying that I don't want to, because there may be other people using this computer, I don't want to use more than that much disk space. In this particular case, the scratch file is limited to 222 gigabytes. So actually a little over a terabyte each. Actually, no. So the I/O was a little over a terabyte of I/O. So a lot of the Nastran output sometimes is referred to in words, sometimes referred to in blocks. So it's interesting. I put one slide here to kind of summarize all the different terms. First thing is, what version of Nastran are you running? The next thing is to understand the concept of a word, and that a word is either 4 bytes or 8 bytes. The buff size is the number of words in a block meaning the chunk of data that's being written. And for a small model, there's some inefficiency in making your blocks too large. But the fact is, for most models these days, the recommendation is if a model is more than 400,000 degrees of freedom, and I rarely see a model with less than 400,000 degrees of freedom, the recommendation is that you use the maximum buff size. Okay, the maximum buff size turns out to be 65,537. For some reason, it's actually 36 that it uses, multiplied by 8. It works out to be half of a megabyte. So that means that Nastran is writing data in and out in chunks of half a megabyte. And you want to make that as large as possible, and that is as large as possible. The SMEM, that's the memory reserved to write scratch files, and that's one of the things you can really do to make things as fast as possible, is use as much SMEM as possible. What that means is that the files will never actually get written to disk, they'll just get written to RAM, which is very fast. The buffer pool is a memory reserved to cache the writing, and that doesn't need to be particularly large. The high core memory is not something you specify explicitly, but it's when you subtract everything else is what's left over. That's what's left over for in-core operations. And then we have 2 scratch files, and these are the files that have most of the I/O. So if you don't have enough RAM to avoid I/O completely, what you want to make sure of, and we'll talk a little bit about this, is make sure those are as fast an I/O as possible, DBAL, and then we talked a little about DMAP. So I can see that I've only gotten a little bit less than halfway through the presentation, and we're almost done. But I'm going to go ahead and talk to you about how you control your I/O. So the other thing that you want to do is you want to make sure that these files that you write, if you can't avoid writing them, that they are written to a fast local disk. Okay, the worst thing you can do for Nastran performance is, most of us run on a network where we have some local disk on a computer, but then there's typically a network drive. And the default, and often our jobs are, we start them off on a network drive because that's a shared drive that everyone uses. And if you just use the defaults in Nastran, it'll write all these files to your network drive. And that will not only slow down your network, but that also will typically be the slowest I/O you can get. Okay, so what you want to make sure of is that these files are written to as fast a disk as possible, the fastest being RAM, that's your actual local memory, and that's what you do by using the SMEM. Okay. If there's not enough memory, the next fastest thing is to have a local solid-state disk. Solid-state disks have faster I/O than spinning disks. Okay. If you don't have a solid-state disk, then the next best thing is to actually have a local hard disk, meaning a hard disk on the computer that's running Nastran, that's not running across the network. Okay. And the worst thing you can do is write those files across the network. Okay. So the number one thing you can do to run Nastran is to think about where this I/O is being done and try and make it as fast as possible, okay, by using as much RAM as possible, and then try and go down this hierarchy of speed and avoid getting down to the point where you're writing these files across the network. And I've got until 10:30. There is a lot more information here, and I'm happy to stick around and answer questions. I will put this slide package up on our site. There's information on here that talks a little bit more specifics. It actually talks about Nastran direct solutions versus iterative solutions, and the fact that under some circumstances you can get, for static solutions, you can get dramatic speed up by using iterative solution instead of a direct solution, not under all. And it also talks a little bit at the end about shared memory processing versus distributed memory processing. These are 2 methods for parallel processing implemented in NX Nastran. It talks about the difference and some of the performance issues associated with those 2. So since I've used up my half hour, I'll turn it over to see if there are any questions.
Does this presentation deal at all with multiprocessors, and in particular multi-machine multiprocessing?
It does, and that's actually the last part of it. So if I had probably an hour, it's an hour and a half, it would. And I will put those slides up there. So it talks about, for instance, shared memory processing versus distributed memory processing. And when you start to talk about multiple machines with multiple processors, you moved into the distributed memory processing realm. And you could probably teach a full 8-hour course just on that, because there's so many different ways of doing distributed memory processing in Nastran. And in this particular slide package, I talk about the RD modes method for calculating modes of a very large model. And that is it is a method that works very well under distributed memory processing. But yeah, it's important, any desktop these days has multiple processors or multiple cores, Nastran, if you just say SMP equals 6 or SMP equals 4, it will use those multiple cores, but that typically doesn't give you that much speed up. If you've got a cluster, moving over to distributed memory processing can give you dramatic speed up, but it is very complex, and there are many, many aspects to doing distributed memory processing.
Okay, well, this is Dan Morgenthaler from United Launch Alliance, and we are definitely interested in that. I'm wondering if you'll be giving any kind of presentations on that subject, or if there's anything that we could do to kind of collaborate with you.
Well, it certainly is. I mean, one thing I can do is I can find out. Well, the first thing I'd say is that the installation and operations documentation that comes with NX Nastran has a pretty good overview of distributed memory processing and the different methods available. What makes it complicated is that there are so many different methods for doing it. I mean, there's frequency domain decomposition, there's geometric decomposition, there are specific methods like RD modes for modal calculations, which is an AMLS type methodology. That's a really good place to start. I will, in fact, if you want to email me, you're welcome to email me, and I'll just send you the slide package directly, but we'll also make it available on our website, and there is some information on the back. The last few slides actually talk about distributed memory processing. And yeah, I'm happy to have a conversation with you. So I guess I'd encourage you to just go ahead and email me, and we can talk more about that.
Right.
But it is very complicated. There's a lot of complexity to doing distributed memory, even just getting it set up to work in the first place. So I assume you guys probably
we found that out, and hence why we want to have this discussion. So
yeah, that's right. I mean, you have to have MPI set up and running. So I mean, you not only have to have Nastran, but you have to have MPI set up and running and all the different nodes and
yeah, and there's certain settings for that particular MPI that need to be optimized and all kinds of stuff.
Right.
We're having issues.
Yeah, you are. Okay, well, I definitely encourage you. We have had some, we do have a cluster here, and we have not, we've actually set it up and we have run the distributed memory processing. We actually don't use that on a regular basis. We haven't had a need to do that, but, and I did find out it's not something that runs out of the box.
Yeah, hence what we're finding and why we're asking questions.
Yeah. Okay. Well, so I suggest we probably discuss some of those things offline. Are there any other questions?
There was a link, a web address for the slides at the first slide, I think. You need to provide that again, or could you provide that again?
Oh, yeah. Let me go back to the beginning.
Or will you email this?
Yes. Do I not have my email here? Oh, that was stupid of me. Okay. Well, what we'll do is I believe that we actually have emails of everyone who registered. So what we'll do is we'll send you an email with a link to my email address and also to the location of the slides. So we'll make sure everyone has that. I didn't realize my email address was not on this front page. But yeah, the other email addresses, these are the two websites. So the website that's specific to the NX Nastran stuff is www.ata-plmsoftware.com, and that's the website you went to register for this for the seminar. Okay. Well, if there are no other questions, I thank you all for your attention. I certainly appreciate that. And as I said, we will make sure to send a follow-up email with links to the slides and also to my email address. Please feel free to contact me.